Okay, okay, good morning. Okay, so thanks for coming in a rainy day. Okay, so today we will talk about the last thing about, please come on in, about functions. So this is the question we have not asked, we have not answered in the last lecture. So we are asked how many surjective functions are there. So surjective means that the codomain needs to be all covered up. And then we want to count, okay, how many of them from a set A to a set B such that the size of A is equal to M and the size of B is equal to N. But then we have to have M is greater than or equal to N. The reason is that if there are not enough elements from A, there is no way that the codomain will be covered up. So in that case, for the case when M is less than N, then the number of surjective functions is equal to 0. Now we have talked about a special case already, the case where M is equal to N. That means that we have exactly the same number of items in A and the same number of items in B. So in such a case, a surjective function must mean it is a bijection. Is that okay? Because each item has to map to each item in the codomain. Otherwise, the codomain cannot be covered up. So in that case, when M is equal to N, we are asking how many bijections are there, and it is simply M factorial, because each bijection turns out to be a permutation of the items of A. Is that okay? Now, let us try to find out how. So there is no very good rule of producing this number in terms of M and N, but we will still see some of the properties of it. So first of all, let's focus on some simple case. Okay. So when N is equal to 1, that is what? That means that so you have a lot of items from A, and then you have just one item in B. So how many surjections are there? So it is easy, because each function must map each item of A into B. Is that okay? So in that case, the number of surjections turn out to be simply 1. So this is the simplest case. Okay. Now let us do a more complicated case. So let's say N is equal to 2 this time. So what will happen? So we still have A is like this. So let's say this time, let's say we have A, the size of A is equal to 4. Is that okay? And let's say the size of B is equal to 2. So how many ways can we map items from A into B such that all the items in B are covered up? So first of all, let us don't count how many items, how many surjections. Let's count it more. How many different kinds of functions can we form from this A to B? How many functions are there? Each function must map an item here to one of the items here. Is that okay? So there are 2 choices for this one, 2 choices for this one, 2 choices for this one, and 2 choices for this one. Is that okay? So the total number of functions is equal to 2 to the power 4. So there are 2 to the power 4 functions. Okay. Now, most of these functions are surjections, but there are some of them, they are not surjections. In particular, there are some functions that map every item into this node, or that maps everything into this one. Is that okay? So we need to minus 2. Is that okay? So it turns out that the number of surjections is equal to 2 to the power 4 minus 2. 2 to the power 4 is the total number of functions that we can form. And then minus 2 is we need to deduct the 2 functions that are not surjections. Is that okay? Now let's get to something more complicated. So when N is equal to 3, what will happen? So let's still have the size of A, let's fix it to be 4. So let's say the A is equal to 4. Okay, this time the size of B becomes 3. Okay, so let's go over the same logic here. Let's go over the same logic here. So we hope to count the total number of surjections, but we do not count it directly. Let us count the total number of functions. How many are there? So how many functions are there? So there are going to be 3 choices for this one, 3 choices for this one, 3 choices for this one, and 3 choices for this one. Is that okay? So the total number of functions turned out to be 3 to the power 4. Is that okay? But now we have to minus what? Minus what? Minus the case where maybe we are just using these two items. Maybe we are just using these two items, or maybe we are just using these two items. Is that okay? We should minus the case that we are just using two items out of three items. So we should minus 3, choose 2. The number of ways that we can form surjections with two items. So in that case, this is this number. Is that okay? Okay, so that's more complicated. So let's don't do that immediately. So we should minus the case where what? Where items can be mapped to only these two items. So these are the functions that we do not want. These are the functions that we do not want. These are the functions that we do not want. How many functions are there? 3, choose 2. And then each one of them is 2 to the power 4. Because this, if I do not use this one, there are 2 choices for this one, 2 choices for this one, 2 choices for this one, and 2 choices for this one. Is that okay? Is that okay? If I do not use this one, 2 choices for 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 this one. So we have so far up to this one. But now we have actually over deducted. So total number of functions minus these many, but we are minusing too much. We have to add back what? We have to add back what? Add back the case that, because when we are talking about two functions, okay, so 2 choice, 2 choice, 2 choice, 2 choice, but they may not be using actually these two at all. Some of them may just use this one, and some of them may just use this one. Is that okay? So we have to add back, actually, we have to add back this one. 3, choose 1, 1 to the power 4. And this is the formula. Is that okay? So actually, let's count it. So here, 2 to the power 4 minus 2 is equal to what? It's equal to 14. And 3 to the power 4. Yeah, so this is, what is 81 minus 48, 3 plus 3. So it is equal to, is equal to what? 36, thank you, 36. Okay, is that okay? In fact, let's confirm our calculation. We can confirm it. Let's try n is equal to 4 for our case. Let's see whether we really get n factorial. Because when n and m are the same, we should get the same number. So this time n is equal to 4. So A has 4 items. And then B has also 4 items. Okay? And at the beginning, we know that the number of surjections turned out to be, it should be equal to 4 factorial. And it is equal to 24. But let's double check whether our way of finding things, is it the same? So we want to check whether it is the same as what we do this by inclusion and exclusion. So in that sense, we need to calculate 4 to the power 4. Is that okay? Is that okay? Minus 4, choose 3, 3 to the power 4. Yeah. And then plus 4, choose 2, 2 to the power 4, and then minus 4, choose 1, 1 to the power 4. Actually, in terms of inclusion and exclusion, we should have another term here. But then it should be 4, choose 0, 0 to the power 4. But it is 0 to the power anything, so it is 0, so it is gone. So we don't write it down. So let's double check it. So 4 to the power 4 is equal to what? 2 to the power 4 is equal to 2 to the power 8, right? And 2 to the power 8 is equal to? Close. Okay, 256, right? 256. And then this one, 4 times 81. 4 times 81 is 324. Okay, very good. 324. And then let's add back. 4 choose 2. 4 choose 2 is 6. 6 times 16, right? 6 times 16 is 96. And then minus 4 choose 1 is 4, 1 is 1, so it is 4. Let's do the calculation. So when we add these two, we should get, no. How should we do things? Wow, difficult, right? So what should I do? Yeah, let's add things. Yeah, two. Anyone has a calculator? Oh, let's do this. Don't be lazy, okay? So what should we add this to? It is 352. Am I correct? If I add these two, is it? These two, if I add it, so it is 352, and then we minus 324 and 4. We minus 328. Oh, bingo. Okay. So this is what we want. It is exactly 24. Is that okay? Is that okay? Okay, so this is a way to compute how many surjections, how many surjective functions using the principle of inclusion and exclusion. Well, this is complicated, right? Complicated. So let's do this with another method, okay? Another method, I love it a lot, okay? But to do with another method, we need to solve another problem, okay? So we need to solve another problem of, so suppose that we have n distinct balls. So balls are distinct. Balls are distinct. And then let's say we have R non-distinct boxes. Okay, we want to count how many ways to put these balls into boxes such that we don't have any empty boxes. So no empty box. So how many ways are there? So we have n. So we can think of the balls are having labels like 1, and then 2, and then 3, and then up to n. And then we have boxes, 1 box, 2 box, 3 box, and then there are R of them. How many? How many ways to put balls into boxes such that no box is empty? Let's do the simple case first to understand what it is counting. So let's say R is equal to 1. How many ways are there? Okay, so let's say n is equal to 4. So in that case, how many ways? So we have 4 balls, right? We have to use up all the balls. So I should say, we have to use up all the balls and no box can be empty. And there are just 1 way. Because we need to put everything into the same box. So there are 1 way. Is that okay? R is equal to 2. R is equal to 2. N is equal to 4. What will happen? R is equal to 2. N is equal to 4. What will happen? How many ways are there? So there are 2 balls and there are 4 balls, right? No box can be empty. So we may have what? So this is already very difficult, right? So we may have, so there are 2 boxes, right? We may have 1 here and then 2, 3, 4 here. Is that okay? We may have 2 here and then 1, 3, 4 here. And then we may have 3 here and then 1, 2, 4 here, right? We may have 4 here and then we have what? 1, 2, 3 here. Is that all? No, we can have 2, 2 division, right? We may have 1, 2, and then 3, 4 here, right? And then we can have 1, 3, and then 2, 4 here. and then we can have 1, 4, and then 2, 3 here. Is that okay? And that's it. That's it. Okay, the other cases are like this. Is that okay? Symmetric. Is that okay? So there are going to be, number of ways is going to be 7. Is that okay? 7 for this case. Now, what is the relationship of this problem to the counting the number of surjective functions? What is the relation? So this problem cares about what? Cares about which balls are put into the same box. Am I correct? Right? So for a function, we care about 2 things. Which items have the same function value, and then what is the corresponding function value? Is that okay? So, do you understand my point? Okay. So, for instance, if you have a surjections from A to B, such that A has 4 items, and then B has 2 items, you can think about this as the first ball, think about this as the second ball, think about this as the third ball, think about this as the fourth ball, think about this as box 1, and think about this as box 2. Is that okay? Think about this. You can think about like this, and then for surjection, it is like maybe 1 maps to this one, 2 maps to this one, 3 maps to this one, 4 maps to this one. It will correspond to a case where we are putting 1 here, we're putting 2 here, and we're putting 4 here, and we're putting 3 here. Is that okay? Is that okay? So each surjection, you can describe it in 2 ways, in 2 steps. First of all, tell me which values are put into the same box. And then the second one is, for each box, tell me what is the value. Is it 1, 2 here, or is it 2, 1 here? Is that okay? Okay? Is that okay? So let me define, okay, the number of ways here. So how many ways are there? So let me call the number of ways here a special number that is depending on n and r. Okay, so let's call it, give it a special label. Let's call it n r with this brace. Is that okay? So it is to distribute n balls, distinct balls, into r non-distinct boxes. Then we can have this relationship. This is the observation or theorem. Okay, observation is the number of surjections from A to B with A is equal to m, B is equal to n, and then m is greater than or equal to n, is equal to what? Equal to, it is looking like we're distributing m balls into m boxes. Is that okay? First, and then tell me what is the label of each box. So it is multiply this with n factorial. Is that okay? Does that make sense? Does that make sense? To count the number of ways to do the surjection, it is first to count the number of ways to distribute balls together. So we have n groups. And then this tells us the grouping. It doesn't tell us what is the value of this one and what is the value of this one, right? So we need to further multiply this with n factorial to understand, okay, this group belongs to 1 and this group belongs to 2. Okay. Is that okay? Okay. So if you understand this, so that's why what? So that's why when nr is 4 and 2, we get 7 here. We get the corresponding 14 over there, because it is going to be 7 multiplied with 2 you get 14. Is that okay? So let's do one more to confirm our understanding. Let's do one more. Okay, so this time, let us try r is equal to 3 and n is equal to 4. So we count the number of ways of putting 4 balls into 3 boxes. Now, it looks like more complicated, but it is not. Because now we have many boxes. We have 3 boxes. We can't have them empty. So there are how many ways are there? Either, so they can't be empty. So each box has 1 ball at least. And there are 4 balls together. So it must be 1, 1, 2, the distribution. 1 box has 1 ball, 1 box has 1 ball, and the remaining box must have 2 balls. Is that okay? Okay, so what can happen for the remaining box? Either you may have 1, 4 as together, or maybe you can have 1, 3 together, you can have 1, 2 together, you can have, this is the remaining box, you can have 2, 3 together, you can have 2, 4 together, and then you can have 3, 4 together. Is that okay? So these are the 6 different cases. So 1, 4 together, it means that 2 is in a single box, 3 is in a single box. 1, 3 together, it means that 2 is in a single box, 4 is in a single box. 1, 2 together, it means that 3 is in a single box, 4 is in a single box. Is that okay? So here it is 1 here, 4 here, 1 here, 3 here, and then 1 here, 2 here. Is that okay? So in this sense, the number of ways turns out to be how many? There are 6 ways. Is that okay? And then how do we get the corresponding case when n and m is equal to 4 and 3? So in that case, we should multiply this 6 with 3 factorial. Okay? 6 multiplied with 3 factorial is 6 times 6, it is 36. So we get 36. Is that okay? And finally, when r is equal to, so this is that okay? So finally, the last case, it will be very simple. When r is equal to 4, n is equal to 4, so you have 4 boxes. So you have 4 boxes, you have 4 balls. No box can be empty. So the number of ways must be 1 here. Is that okay? And then to get the corresponding value of the number of surjections, we multiply 1 with 4 factorial, so we get 24. Is that okay? If you understand what I'm talking about so far, could you please raise your hand? Okay, this is difficult, really difficult. So don't worry if you don't understand. Yeah. Watch the video again. Okay. Yeah, but here, these two. Okay, so here I want you to understand that for the same problem, there are 2 different ways of solving it. One is we can do this by inclusion and exclusion. And the other is you can transform this into a different problem like this. But why? What is the benefit of transforming into a problem like this? What is the benefit? If you look at it, we are still listing out the cases one by one. Now, but I love this method a lot. It is because there is a very efficient way to find out what is the value of this nr. Okay, so this is what I'm going to tell you now. Okay.